Hi, good morning all. My name's Andrew, and the other members of my group are Nicholas, Pranav, Lewis, and Ita. The title of our group project is Aligning Moving MRI Images with the Power of Deep Learning. The problem that we're trying to solve occurs in a clinical context. More specifically, it occurs in the obstetrician's ward when MRI scans are being taken. MRI machines are these large wide machines that you see in hospital, and essentially what they do is that they take multiple 2D scans and try to stitch them into a single coherent 3D whole. The problem that we have is that, as you can imagine, fetuses do not listen to instructions, so any movement by the fetus in the womb creates motion blur, which is problematic for clinicians trying to view the final 3D image. We have on hand a series of third-party libraries that can help to correct for the motion blur and produce a much better final image. I will now showcase a before and after to demonstrate the benefit that our software can have on correcting motion blur. So this is an image of a baby's brain before processing. On the right hand side you can see that this is a 3D image of the MRI scan. And on the left hand side, you can see I'm showing you the baby's brain here on the green plane. So in particular, if you look, when I scroll along the green axis, you can see the distortions that are being introduced in the process due to the movement by the baby. And the quality of the output image here is not particularly clear. So that's the problem that we're trying to solve. I will now show you an output image from one of our libraries, NiftyMic, and compare that. So this is an image after processing by one of our third-party libraries, NiftyMic. Again, on the right-hand side, you can see that this is a 3D image of a baby's brain, slightly more zoomed in for reference. And on the left-hand side, you can again see the image along the green plane here. So you can see that as I move along the green axis, you can see that the baby's brain is much clearer and that there is substantially less distortion as a result of the processing. So that is one of the benefits of our software. And I will now talk about our scope of work and what we've done to actually extend this project to make it more widely available for end users in a more convenient fashion. Broadly speaking, I've classified our scope of work into three separate categories. The first is maintenance, the second is improving accessibility, and the third is evaluation and analysis. Firstly, in terms of maintenance, we were tasked with updating the CUDA C code from version 6 to version 10.2. We also created a run script for the SVRNet deep learning library. Second, in terms of accessibility, we Dockerize all of these third-party libraries because Docker ensures ease of use and installation across multiple platforms. We also have a backend pipeline so that users could run custom options using these third-party libraries. We hosted all of these solutions on the cloud because these applications are extremely GPU intensive, so we wanted to utilize the power of cloud computing to process these images more quickly. Lastly, for accessibility, we also built a front-end user interface both in the form of a desktop and a web application. Ultimately, this means that end user does not have to interface with the command line, but can simply drag and drop the images for processing and download the output files. Finally, in terms of evaluation and analysis, we wanted to go beyond the human eye to ensure that we could objectively measure the quality of our outputs. So to this end, we built an evaluation script for the deep learning predictions from SVRNet. I will now hand on my time to Ita, who will talk about accessibility and more specifically, the building of the backend pipeline.
Thanks, Andrew. So now I'll be briefly going through the pipeline script which drives the back-end image reconstruction process by providing a wrapper around the three software packages, SVRNet, FetalReconstruction, and NiftyMic. So this is the general execution flow of the pipeline. We start off with a number of corrupted Nifty images. These are fed through a program called Fetal Brain Seg, which generates a mask for every image that isolates the position of the fetal brain within the image itself. The masks and the images are then fed through SVRNet, which performs coarse grain realignment. SVRNet is optional. It's only required if the original images are extremely corrupted. Next, the images are fed through either FetalReconstruction or NiftyMic, both of which perform fine-grained realignment to eventually produce one final restored Nifty image. So now I'll just show a short demonstration to see how the script works. As you can see, this is the command that we use to invoke the script. We have an input flag -i, where the user can indicate the input files, -o an output flag, where the user specifies the output name, and then 3 flags -n, s, and f, each which represents one of the software packages. So these are used by the user to indicate the configuration of the pipeline that they would like to run. I will just use -n for simplicity in this demonstration. So it says we are running the container for fetal brain sag, and the reason for this is because each software package is contained within its own Docker image. And this is useful for dependency reduction because every Docker image contains the complete environment that allows each software package to be run. An alternative for dependency management is a virtual machine, but virtual machines are a lot more heavyweight than Docker containers because a virtual machine will have to run its own operating system, whereas a container is much more lightweight since it uses the underlying OS of the host machine that's running on. So as we wait for the script to finish running, I'll just quickly go through some of the challenges that we faced as we wrote the script. So the first challenge was how to retrieve output from a Docker container. This is necessary because any files created within a Docker container will be destroyed once the Docker container has finished executing. And so the way that we found out how to do that was to use a Docker feature known as a bind mount, which basically allows us to mount a directory from the host file system into the Docker container. This allowed for persistent storage. The next challenge we faced was how to redirect input and output between containers in the pipeline in a clean manner. And how we chose to do this eventually was to have the script create a central folder where all input and output files related to the pipeline will be stored. And this one folder will be mounted into every single container to ensure continuity and access to the same files. Eventually, the output file would be copied out of that folder into the location specified by the user before the entire folder is deleted. So now let's see if it's completed. Okay, so the process is completed. If I run ls, we can see that out.nii.gz has been saved. And if I run docker ps-a, we can see that no containers are currently running and all stopped containers have been removed as well. So that's all for the pipeline script. I'll hand over my time now to Pranav, who will be going through the web-based graphical user interface.
Thanks, Yide. I'm now going to talk about the FetalReconstruction web GUI, which is basically a web application that runs in the browser and allows the user to simply run the pipeline at the click of a button. To start the web app, we first need to spawn the Streamlit web server. So first we cd into the right directory, and then we do streamlit run sltest.py. But in the meantime, I'm going to tell you about ZeroTier, which is a global area network which connects just different nodes to the same network, even if they're not connected on the same LAN. It's very easy to use. We can see the network details using this menu bar, and we can also join the network using this option here. It's very simple to set up, and you can manage access on the portal, so only authorized nodes can access the network. So now we see the Streamlit web app is running, and ideally this would be running inside Google Cloud, but for the sake of this demo, it will be running on a local machine. Now I'm going to show you how the web app looks. So you can see here that the Fetal GUI web app has a simple drag and drop interface to browse the files, select the packages, and to run the package, and finally download the file. So what I'm going to do is I'm going to first browse the files on my local file system. So I'm going to upload this file here, which is a Nifty file, and we wait for this to upload. So this you can see is top right, and while this is loading, user interaction is disabled on the web app. While it's doing this command, we can see in the Streamlit server logs what's going on. So you can see here that the first command is making a directory in the input files directory using the anonymized session ID, and we've also got this browser storage uploaded file uploading to the web server. So this is in Google Cloud. If we go back we can see that the output was successful, so the status code of the commands were both 0, and this is the path of the browser store. Now, if we select a package, let's say FetalReconstruction, first we wait for the UI to update, and then we can run the package. Note that in order to connect the Google Cloud to the same global area network, we can automate the joining process using a script. Now, the script itself uses a client called the zero-tier CLI, and it's very simple to use. You install the dependency, and then you run zero-tier CLI join E4DA7455, which is in this case the network ID. If I click this, we wait for it to execute, and then finally it will return to us a status code telling us the status of our connection. And you can see that it joined successfully. Let's go back to the Streamlit web app. So you can see here that we've transferred the files to this directory. Now if we go to the web app, we can run the package. And you can see in the top right it's loading again. We have to wait a small amount of time for it to load. And usually this depends on the network connection speed. Usually it will only take a few seconds. And you can see the package itself being run is this command here. So first of all, we're running the run scripts using these input parameters, which is the anonymized session storage, and outputting it into the output file here. And once we've got the run script running, we have these input parameters and the SSH key file. So all of this is highly secure. You can see the output of the running the package was 0, which means that it ran successfully. We can now download the file, and this will again take a few seconds, but once it's done, we'll be able to see the file in the file manager or the finder. So let's see the command which is running. So you can see we're SCP the file back to this directory here, and once it's done, you can see the status code is 00, which means that the output image was saved to the browser storage and also to the home directory. So you can see that here, testoutput.nii.gz in the output images folder. So now we've seen the web GUI, how it looks in the browser and how it works on the command line. This is a simplified system diagram which shows you visually what's going on. So first of all, we have the motion corrupted images. We upload these to the web browser using SCP. And then once they're in the web browser storage, we upload these to the web server and also using SCP. Once we've run the pipeline using SSH, we download the output files using SCP, again using 2 hops, back to the local machine. So why build a web GUI? A web GUI makes it easier for a non-technical user to run the pipeline. The only requirement is an internet connection, and there's no need to use complex terminal commands or understand the inputs between stages. Using zero-tier makes it simple to manage users and make open access to the website. By using a VPN, you can also hide the port, exposed SSH port, on the local machine and protect against network attackers. Using the GUI for the zero-tier application is very simple, and it makes it possible to connect many nodes onto one network seamlessly. How did we build the front end? The front end was built in Python and uses a Python library called Streamlit for the web UI components. Python was used because of its ease of development and also its many libraries to support the web app. One particular library we used for networking was called subprocess, and this allowed us to spawn concurrent SSH sessions at the same time and allow multiple user management. We also made anonymized session storage using the UUID library. The backend was hosted with Google Cloud and ran the Dockerized pipeline as mentioned by Yide previously. It was very complex to set up for a simple user, so it was automated through the use of a Docker file and a run script. I'll now pass on to Nick, who will explain the evaluation script which evaluates the output image from this pipeline.
So let's look at some motion corrected output examples. Which of these two do you think is a better motion corrected output? It is obvious that the left image is a much better motion reconstruction than the right image. So it seems that just by visualizing the image, we're able to tell which is a better output. So why then do we need the evaluation script? This is because of similar quality images. Let's now take the top pane, for example. Which do you think is a better image? It's hard to tell just by looking at it, and what you think is a better reconstruction might not be what another person thinks is a better reconstruction. Therefore, we need a more objective way to evaluate our outputs, hence the evaluation script. But how exactly does this evaluation script work? So what we do is that we actually take in the input 3D volumes that were used prior to the motion correction process. And then we also put in the output that was created by the motion correction process. Lastly, we include the motion correction parameters. What exactly are these motion correction parameters? These are basically how each of the layers within the original 3D volume has adjusted to create the motion corrected output. By putting these three inputs into our program then churns out these two indexes, the PSNR index and the SSIM index. So let's look a bit more at what these two indexes mean. PSNR and SSIM are basically measures of similarity between two images. For those of you who have taken the machine learning course, a high PSNR basically means that there's a low mean squared error. This implies that two images are more similar. PSNR ranges from 0 to infinity. On the other hand, a high SSIM also means that two images are more similar, but SSIM only ranges from 0 to 1. The main difference between these two indexes are basically the definitions of what similarity means, but discussing this would be way too technical. Let's just look at a few examples. From this, we could see that dogs that look more similar and cats that look more similar have a high SSIM score and a low MSE score. A low mean squared error implies that there's a high PSNR. On the other hand, cats that don't look that similar have a low SSIM score and a high mean squared error. This means that they have a low PSNR. So how do we use the similarity indexes for our specific case? There are two main issues that our group face. The first issue is that we have multiple inputs and only a single output. Without a one-to-one mapping, it is hard to tell how similar the output is to the original input. Next, each of the layers have been rotated to varying degrees, and therefore, it is hard to compare, again, the similarity between two layers. So what we basically did was we reversed the transformation and we recompared each layer. Let's take a closer look at the process. So this is basically the inputs that went into the nifty make library, and then it came out with a reconstructed output. So there are some transformation parameters that have been applied within this process. We reverse this transformation by reversing the transformation parameters here to create this resampled volumes. So this now becomes comparable to this. Then the next step is simple. We just break it into layers, compare each layer, get a SSIM and PSNR score, and we just mean it. So that's it for the evaluation. I'll now pass the time over to Lewis, who will do the conclusion.
Thanks, Nick. So in this part, I'll quickly talk about our achievements and learning outcomes from our project, and then I'll talk about further extensions. So to summarize this slide, we built the pipeline using CMake, Docker, CUDA, and also Python shell command. And then we evaluate the output images using TensorFlow and SimpleITK. With the graphical user interface, we used Python Tkinter library to build the prototype of GUI on local machine. We extended further to build a web GUI using Streamlit. And then we host that web GUI on Google Cloud with GPU-enabled machine. And finally, we used Python subprocess to spawn concurrent SSH session and transfer file with SCP. So how can we extend our product further? We can switch from Google Cloud to AWS Spot Instance, which means that we can shut down and spawn instances dynamically, meaning that more users can access our product at the same time. The reason that we didn't use AWS Spot Instance for our project was because it wasn't available for free for students. We can also integrate MITK with our web app to provide a good visualization of the outputs after the image processing. And lastly, we can also fix the compatibility issues between different external libraries. During our project, we believe that fixing the problems would involve understanding the deep learning algorithm of the third-party libraries, and also because the codebase is very large, we decided to invest more time on the GUI and evaluation script instead. And that's the end of our presentation. Thank you very much for your time, and we are happy to take any questions about our project.